This is group A2, and we are presenting sets, their unions, intersections, and generalized unions and intersections. A set is an unordered collection of objects. The objects in a set are called elements or members of the set. The set is said to contain these elements. If an element exists in a set, we use this symbol to show that it is an element of the set. If an element is not part of a set, we use this symbol to show that.
You can say that A exists in the set S, like so, or that B does not exist in the set S, like that.
You can list the elements of a set like so. A is the set containing the elements 1, 2, and 3, where B is the set containing 1, 2, 3, and all the numbers up to 99. The ellipses denote this. A set does not have to contain numbers. It can even contain letters or any other type of object. A set can even contain other sets. There are some common sets, and they are denoted with certain letters. For instance, N is the set of all natural numbers. Z is the set of all integers. Q is the set of all rational numbers. And R is the set of all real numbers. A plus or minus can be added at the end of these letters to denote whether the set contains the positives or the negatives. We will now move on to the union of sets. Let A and B be sets. The union of A and B is the set that contains all elements that are in either A or B or both. We can use this symbol to denote the union between two sets. Venn diagrams are often used to show the union and intersection between two sets. This is the union of set A with set B. Note that it contains everything in both set A and set B. Here is an example. We have set A, which contains 1, 2, and 3. Set B contains 1, 8, and 9. The union of A and B contains the elements 1, 2, 3, 8, and 9. Next, we have the intersection. The intersection of a set can be denoted by the symbols shown above the Venn diagrams. Once again, Venn diagrams are a common way to denote or to show the intersection of sets. This is the intersection between set A, set B, and set C. It is only the area that is contained by all of these. Next, we will move on to the generalization of, an example of the intersection between sets. For instance, we have A is the set containing 1, 2, and 3. B is the set containing 2, 4, and 6. The intersection between these two is the set containing 2, because it is the only element in both set A and set B. Next, we will move on to the generalization of unions and intersections. The generalization can be written as follows. This represents the union of the sets A sub 0, A sub 1, all the way through A sub n. Next, we have the generalization of the intersection. As you can see, it is denoted by the symbol shown, and it is very similar to that of general unions, except that it is now the intersection of the subsets A sub 0, A sub 1, through A sub n. Here are some examples. Let A be the set 1 and 2, and B be the set 3 and 4. A sub 2 be the set 4 or 5. B sub 2 be the set 6, 7. A sub 3 be the set 8, 9. And B sub 3 be the set 3, 5. We will do the union with A and the intersection with B. To do this, we first write out the symbol, the union with I equaling 1 to 3 of A. Now if we go back to our previous slide, we can see that A contained A sub 1 contained elements 1 and 2, A sub 2 contained the elements 4 and 5, and A sub 3 contained the elements 8 and 9. So their union of A sub 1 and A sub 2 and A sub 3 will contain the elements 1, 2, 4, 5, 8, and 9. A very similar procedure can be followed for the intersection of B. I equaling 1 and n equaling 3. Now if we go back, we can see that B sub 1 contained the elements 3 and 4, B sub 2 contained the elements 6 and 7, and B sub 3 contained the elements 3 and 5. The only element that repeats is the element 3. So in the intersection of all of these sets, the new set contains only the element 3. We can also show the difference between two sets. Take, for instance, you have set A that contains the elements 1, 2, 3, and 4. Next, you have set B that contains the elements 1 and 3. A minus B results in the set 2, comma 4. This is the basics